Welcome, everyone. I'm going to talk to you today about Cython, specifically with the following topic of revisiting Cython. Is it still effective? Um, Once upon a time, a long time ago, July 2020, I gave I guess, the intro to this topic, my first explorations into it. And so the motivation for this talk is to kind of see what has changed in the last almost 5 years. Somehow, time flies. See what just as different, both in Cython and in how people work in general. Okay. So today's aim, we're going to discuss some core concepts. So for the computer science people in the audience, that's complexity and types. For the non-computer science people in the room, I'm going to do my best to get everyone just on the same page and give you some formal definitions you can use for today. They won't hold up to intense scrutiny, but they're good for today. We'll talk about Cython and how it works. We'll get into the changes in recent years. I'm going to jump into a live demo, which should be helpful for researchers and how to use Cython and how I use it personally. We'll circle back to review and recap what we've learned and what we've discussed. And then I'm going to leave a pretty decent chunk of time at the end for questions because I hope to hear from everyone here. And also, hopefully, at the end of this, everyone will use Cython in their own projects when they need to for optimization. Okay, so some Python commentary. I don't think this slide has changed much in 5 years. Python sure is awesome, but awesome isn't free. Okay, I think we can all agree. I don't know about you. I'm the person at SharkNet who kind of is the lightning rod for Python. Anytime somebody complains about Python, they also poke me and go, "But Python's slow, Tyler." And I say, "Yes, of course, right." But interestingly, even other languages have this narrative. This is a great talk from Chandler Carruth in 2019 about C and C++ and how there are no zero cost abstractions. Even the hyper fast data structures that are super optimized in C++ also have costs. Okay, so Python being awesome to develop in, that is what we get, but the cost is often speed. Okay. But what do we do when we need Python to be faster? What do we do when our job it takes 7 days and that's just not going to cut it because we have 100 runs that we need to do? So in general, if you do nothing, you will just suffer, right? And this is still as true in 2025 as it was in 2020. Nothing has really changed here in terms of Python, sort of. Okay, so let's now just take some time to get on the same page and discuss some principles that Cython takes advantage of, okay? So types and type systems, we're going to discuss briefly. Compiled versus interpreted, why compiled is 99.9% of the time better. And then we'll talk complexity. We'll stay away from big O and kind of, this is n log n or n squared. We'll just talk general terms. And like I have here at the bottom of the slide, these are really sweeping generalizations. So please don't get upset if you're an expert or save your question till the end and we'll talk about it then. Okay. So types and type systems. I've defined a type here today as a known representation of data that has associated operations. So integer, great. We know how to add two integers. A string, adding two strings concatenation is of course different, right? So there's different implementations for those. That's fine. We understand that. Our variables or our structures all have associated types. There's lists as well. Great. We have dynamically typed as a type system for a language. That's Python. Everything is verified at the time, so you check to see if you're adding two integers together, and if not, maybe throw an error, which I have there. You're going to see runtime errors. Um, there is a lot of overhead in figuring this out. There's a lot of safety checking that Python does that you may never see if you're not concerned about speed, to make sure that your development experience in writing Python is really easy to write. Like if you access, -1 an array in Python, nothing bad happens. It's just like, oh, you meant the last element, right? In other languages, the program would just completely crash. Okay. So you have statically typed languages as an alternative. These are your C and C++ languages. Variables and functions have signatures, which define what types they operate on. You basically can't mix and match these types. If int x is an integer 99% of the time, it's going to stay an integer, and that's fine. Okay, because what you get from that is you can do syntax and grammar checking on your program. You can do optimizations, okay, and that's where we're going to get into compiled. But there's less freedom in a statically typed language in general, but you get something from that too. Speed and safe, like knowing exactly what a function is going to do with its inputs. Okay, compiled is faster. Why? This is probably something somebody's told you. Um, I'll take a stab at it here. Compiled code is running natively on a machine from a static source, perhaps a binary, and it can be highly optimized for known patterns or systems. Okay, so if I give you a piece of Python code, it's interpreted, which requires a layer of execution before results are seen. So it needs to be turned into bytecode. It needs to figure out exactly what these variables are as it's doing them, and it needs to be done on the fly slow. Okay, compiled code, you can do multiple passes compiling things and optimize it. Kind of be like, oh, this part of the code runs a lot. This part of the code doesn't. Let's focus here. Let's make, this variable very like easy to get at for the CPU. All sorts of things you could do in a compiled language that you can't quite necessarily do in Python. Okay, like I know that these things exist, but we're making our generalizations. Okay, great. Let's talk complexity. Lastly, here, we're not comparing something formally like big O of n. We're not talking like data structures or anything like that. But I want to talk about what list access looks like in Python. And if you've ever thought about it, I bet you there is extra things, okay, that you're not seeing. So in Python, first thing, make sure the variable that you're indexing with is numeric. That's important. You can't index something with a string in a list. Doesn't make any sense. Next, you got to determine if it's within bounds. Okay, fine. But if it's negative, you have to do wraparound magic. And then sometimes you got to do even more because it might be a nested list. You might be returning list stuff. You might be like all sorts of different things. It might be a range. You might be calling like :-1, these sorts of things. It's expensive. It's great to write code with, and it's really, really freeing, but it's expensive. Okay, let's contrast that with like array access in something like C. You have a pointer to some memory, you know the type of that, and what you do is you compute how far into this section you need to read, and you go there and you just interpret it and you read it and you return the value. That's it. There's no safety checking, there's no magic. This is exactly what you get as you get it. Okay? So, there's large complexity overhead like this abstracted away in Python all over the place. And what we get, again, it's important. We like what we get from that, which is freedom to develop in a really kind of modern way, but the cost is speed. Okay? So one of the popular alternatives to this is in clawing back some speed is something called Cython. It's a superset of Python, so it's Python no matter what, but there's a little bit extra. And the idea is to recover the C-like performance we gave away, but still being able to maybe even start with Python or write with Cython in mind the entire time. Okay. And what it does is it takes Python and it compiles it into C and C++ and lets you call it seamlessly. So you can compile a function into C and C++ and call it, or in a Jupyter notebook, which I'll show you in a little bit, you can call those functions and do whatever you want with them. Okay. And the way that we do all this is we signal to Cython using annotations and type hints what each variable is doing and what the structure of your code is doing. And it will be orders of magnitude faster than vanilla Python, always. Okay? So that all sounds great. And maybe it is. Spoiler, it is. But these four things here are pretty popular. I think we can all agree. And all four of them definitely make heavy use of Cython in their library. Okay? So that's the further justification for you to keep hearing me out and give this a try. Okay, so how does it work? I've said it briefly, but there's three things here that are the biggest focus of today's talk. There's much more you can do, but again, we're going to try and keep it within an hour or less so we can have questions at the end. So we're going to give back some of our abstractions. We're going to compile some Python, we're going to annotate some types, and we're going to talk about memory structures. Okay, so compilation, just by compiling into Cython, we're going to see speed increases. Just by saying when a list accessor is an integer, we're going to see speed increases. And when we change to a memory view, when we change to a different way of accessing the data, we're going to see a huge increase. Okay? And all of that, the speed will blow your mind. Okay? And it's basically for free. So, what's changed since I first gave this talk in 2020, 1700 days ago? I think well over 1700 now. Not too much, honestly. There's better interfacing with Python's native typing. So if you've ever gone and like tried to write strongly typed Python, which is optional, of course, you can do that. Cython will play nice with that now, which we'll see. There's some shorthand annotations for turning off some of the list bounds checking and always checking if your division is safe and so on and so forth. You can turn that off to improve performance now. We'll see that as well. And then um, there was significant. I looked through the change logs itself for NumPy, and there were optimizations for memory views all over the place. So that was a large change. Excuse me. So at the end here, I just have like the open question of, are we forgetting anything? Are there any major changes since 2020 in computing in general? So this is the slide, right? Anyone heard of ChatGPT? We all have heard of it. We're all hopefully using it. It's an important tool in your toolbox now. The release date was November 30th, 2022. Feels about right. Maybe there was some stuff discussed before and after about how you could actually get access. I don't think I got access around then. I think it was later. And we all definitely agree here in this room that it's significantly altered the landscape of computing in general. Things are very different now. It's AI this, AI that. You click on one AI video on YouTube and your algorithm is ruined because of how like dominated it is. Well, dominating it is in like how much there is out there. People are being served this content as well as consuming it. And one of the amazing things about ChatGPT, especially when it came out to me, is how effective it was when working with code and providing solutions. Okay. But I want you to think of annotating code and making brief changes to code as something that like ChatGPT is quite good at. And it makes sense, right? Like if you ask ChatGPT, "Hey, take a look at this code and debug it," it'll do it, right? But if you ask it something similar, "Hey, take this code and add type hints and ask me anytime the type is ambiguous." And so you'll have that conversation, you copy and paste it in, and your function will run sometimes 100 times quicker. Okay. So ChatGPT and other LLM tools like it, Cursor, Windsurf, these kind of AI powered IDEs raise the skill floor of what is possible by a beginner. And this is important. It's my personal belief, we're not all going to be replaced by AI. It's the skill floor is much higher now. So back in the original version of this talk, I placed a decent amount of emphasis on, hey, go learn a little bit of C and C++. It'll take you really far in improving your Python performance. Now, there's less of a burden on a Cython user to do that. You can be taught it by ChatGPT. You could ask it to do it for you and explain the things that it's come to the conclusion of for you. Okay, so that's a huge change because we're all researchers here. Like I had in my undergraduate two or three C and C++ courses exclusively. So like I was familiar with using vectors and generics and all sorts of things. Researchers here today, I assume, have not taken as many C and C++ courses or have taken none, right? So this is great for Cython as far as I'm concerned. Okay, so one of the other things I promised that we are going to do today is a live demo, and I will do my best to do that in front of you in just a second here. Just some quick details. When Sergey uploads the video, I'll have them include a link to my GitHub where I'll have all this reference material, and I'll print some stuff to PDF so you can copy paste from it. I'm going to be using VS Code today with the Jupyter extension. You can use Jupyter Lab like in your browser. You can do whatever you like with that. Um, the package installation notes I'll include with the GitHub link, and it's just one line, a requirements file. Okay. And today we're going to be focusing on three different types of optimization problems that I've picked for us. Okay, so problem one, it's pronounced Levenshtein distance. This is edit distance between two strings. This is a like classic computer science problem. It's dynamic programming. It's got matrix stuff. It's got like array accessing. It's great. Um, it's difficult-ish to program. Like it's not something you could just like look at the definition of and be like, oh, okay, that's how you do it. But I've got one provided, and we'll work off of that for Cython. Problem two, I just realized that my slides are missing what they are. Problem two is I'm exploring a robust statistic really quickly because that's something researchers often struggle with. And problem three, we're going to be talking about the prime sieve, which is from my first talk on this topic. And we'll see what we get from ChatGPT with that problem. Okay, so I'm gonna flip over to VS Code over here. So I'm not gonna talk too much about Jupyter because I talk a little bit more about it in the first video in this series. Percent stuff in Jupyter is often referred to as magic commands or magic cell commands. This one, it's basically the equivalent of importing Cython and allowing us to use use Cython in a cell. Okay, so I'm going to do that. I'm going to do my imports. Nothing crazy here. The plotting is for the problem two in a bit. I'm not going to run my pip install because my environment's already set up. I've tested this. Exclamation mark allows you to kind of access the underlying kernel to run commands. Okay, so let's look at our first problem here. This is the classic implementation of a Levenshtein distance. It's the edit distance between two strings. So I'm not going to give the formal definition for this. I'll just show you with the examples. That's more important. But again, it's a dynamic programming problem on strings. Okay, and so I have four test cases here. Apple and apple, there's no different. Cat and cats, one. These are two completely different strings, so it's four. And then horse, this is the one that gets people, is R and O being switched counts as one thing. So the edit distance between these two is three because deletions also count as one. Okay, and so this is kind of the recursive step. It's what builds out a matrix in dynamic programming. You don't need to know what this problem is actually doing to understand the value of what we're about to do next, okay? So all of that stuff ran very quickly because they're small strings. Now what I'm going to do is I'm going to attempt to do a quick benchmark with another kind of magic cell method called time it. And what I'm going to do is run this on two random strings of length 2000 and see what happens. So those are my two random strings there, quite long, completely random, and we're looking at our timing benchmark here. Okay, give it a few more seconds. It likes to do a couple runs to just briefly measure the mean and standard deviation. Okay, so we get 2.77 seconds plus or minus 18 milliseconds per loop. It did 7 runs. Great. Wonderful. Okay, maybe that's fast. Maybe that's good enough for you. But let's assume that it's not, okay? So what I'm going to do is I'm going to start using Cython now. And I'm going to start by taking this entire cell here and adding double percent Cython, which means this entire cell is now being Cythonized, okay? I'm going to have a new function header, and everything else in here is exactly the same. It's exactly the same. Okay, so what I'm going to do is I'm just going to run that. Okay, it ran. Excellent. Let's just try timing it. It's a brand new function. Let's see what happens. So VS Code is going to go away for a second. Hopefully it's running this now. I think. It looks like it is. Yep. And just like I promised, we've already knocked 0.7 seconds off just by compiling a function. The magic of Jupyter Lab in this instance is compiling all of this behind the scenes and making this function header available to you to call as a C and C++ function with your Python. That's great, and we love Jupyter for that. But this is just the first step, right? We can certainly do more with this program, but like this is a win. Like we're already there. If this was your thesis, this is your research project, just making the main meat and potatoes of your program Cythonized is going to increase your performance significantly. And that's going to scale, right? Like that's 2.77 seconds down to 1.99 seconds. Think of that as hours. That's a big difference. Okay? But furthermore, something that Cython provides us is a mode for annotating its compilation. Okay? So by adding -a, what we get is the ability to look at how it is being compiled into C and C++. And so we do that with the -a that I've shown up here above, and it says yellow lines hint at Python interaction. That's bad because that's slower. We know that, we agree on that. Click on a line that starts with plus to see the C code that Cython generated for it. Okay, let's have a look at this first one here. M and N is the length of the string 1 and string 2. Okay, you don't have to understand what is going on in the recursive case down here to understand what's going on there. Okay, wow. So this is all the C++. That's a lot of C++ for basically taking the length on two things. Okay, that's surprising. What's in here? Okay, we're making a new object. Wow, that is a lot for doing a list comprehension. That's crazy. That's so much. Well, okay, these for loops are crazy. This is all overwhelming. Okay, that's a lot. The first step in working with Cython on your projects should be just annotating the types of what you know. That's it. You don't need to go all the way down and understand exactly what's going on here. Wow, like that's tons. Like I can look at it because I've done this for a while now and I kind of vaguely know what it's talking about. But that's a skill set you're going to build by working within this framework over time. Okay? So let's start really briefly by annotating the types that we completely and easily know for free. Okay? And we do that by doing a C import on Cython. So that's a slightly different keyword than import. All it does is basically allow you to start using the Cython keywords. Okay? So if I look at this function, what do I see that I can just like hard code the type for that I know is never going to change? M and N never change, and I and J are just like loop variables in your range thing here, right? So all I'm going to do is say M and N and I and J are all integers. I think we agree. Looking at this, they're all array accessors. Okay, great. Wonderful. Let's time it and see what happens. So I'm going to recompile that function. Okay, the yellow is a little different. It's a little bit better, but there's still a lot of yellow. But let's see what we got from that. Let's run that cell, the timing cell again. Okay, it's running. We were at 1.99 seconds before. We've dropped basically another almost full second. I've added one line that was simple inspection of which things are integers. Again, like this is a huge win. Everyone should be doing this if you just need a little bit more speed. We went from 2.77 seconds down to basically 1 second just by being like, oh yeah, okay, these are integers and they're integers all the time. Okay, so the next thing I want to walk you through is array access. This is a lot of array access. This is building up an array. Okay, that's what it's doing. I'm going to copy and paste these two things in, but I had talked about it previously in my slides. Basically, bounds checking and wraparound stuff in Cython, in base Python rather, is expensive, and so these are new Cython features that allows you to disable that just for this function with decorator syntax. Okay, so why don't we compile that? Okay, nothing really different. Let's run it again. Let's see here. Okay, doing the timing. Okay, no difference. So that's going to happen sometimes. You're going to look at this and you're going to be like, all right, let's try that. But this is the importance of like trying things. Like we'll leave it in. Maybe it'll help in the long term, but right now, not so much. Okay, so what else do we know the type of in this function that we could speed things up with? We have DP, like the big matrix. Okay, that's complicated. We'll do that in a little bit. But the last two things that I see that are basically free is string one and string two, right? What are they? Well, they're both strings. So luckily we can use Python's native like understanding of typing to we'll just say that they're strings. Now, I want you to guess in your head how much you think that that's going to help by. Just guess. Just picture it how much lower we're going to be than 1.12 seconds. Just by being like, yeah, string one and string two are strings. Okay, let's run the timing. It's 700 milliseconds now. Just by making it completely unambiguous that what we're going to be doing is taking the length of these two strings. That's it. We went from 2.77 seconds and we've cut it down to zero point 0.7 seconds just by annotating types. Okay, so hopefully you're convinced, and now I'm gonna convince you further. And this is something where you're building towards a skill set, but we're going to talk about a memory view. We're going to talk about how we turn this matrix into something that's a little bit better to work with. Okay, so I'm going to copy and paste it in because I've got it off another monitor here. And we're going to do two things. Okay, this is how you start allocating a memory view, which is a way for Cython it's a way for Cython to access memory much faster. Okay, we still want our nice syntax doing these things down below, but we want it to be faster. So here's the code words and structures for this. Okay, so number one, we're using a NumPy function. So that's non-surprising, but this is weird. The CNP, what's that? That is from Cython's understanding of NumPy. Okay, so I'm going to put that up there. This is special. Like Cython acknowledges that NumPy is amazing, and so it has special bindings for it. So that's where this kind of comes from. Okay, so what I'm going to do is I'm going to comment out this old matrix structure, and what we've done now is we've made an m by n matrix, and it's of type integer 32. Okay, we need to specify that because I think the default is floats. Okay, now the last step that's very important is we need to signal kind of how we're going to be accessing this big block of memory. And we do that just like this. Okay, this is basically copy and pasted from Cython's documentation, and you'll be able to put this into your own code to use. Okay, so all I've done now is I'm saying it's going to be integers and it's going to be two-dimensional the entire time. Okay, so we run our compile step again. Taking a second here, bit surprising. Okay, we get a bit of a warning. Not sure what that's about, but that's fine. We'll test it later. Okay, wow, like the yellow has disappeared quite significantly. Okay, it doesn't like this, but that's run one time, so we'll ignore it. Okay, that is expensive. Initializing things is always going to be expensive, but our for loop is completely cut down now. That's great. So I want you again in your head to guess how much time this is going to go down to. What we've done is annotated some types. I've copy and pasted in a documentation for making an empty 2D matrix. How fast do you think it's going to be? So we'll run it. 36 milliseconds. This it Everyone should use this when deploying their code in research. From 2.77 seconds to 36 milliseconds. Okay? So our conclusions from problem one, I'll go to it here. Low-hanging fruit from type annotation is basically free, and compilation is also free, right? Bounds checking didn't help. Maybe it'll help in your project, but it's still something we should try. It doesn't hurt, right? Tackling known things like the function header definitions can be really surprising. Like you don't always know what's happening under the hood, right? Like changing things to string there and know like obviously they were going to be strings. You agree? Everyone here agrees. This the speed increases or it can be really surprising. And we did that with Python's native typing, okay? And then memory views are extremely powerful ways to reference data. Okay, I'm going to speed up a little bit on our problems now because we're about halfway through. What I have here is a problem that is based on robust statistics. So a common sticking point for researchers is getting over the burden of starting to use and run robust statistics because it's complicated to program sometimes, and they can be expensive in time and memory to run. Okay, so a robust statistic can be defined briefly as a measure which is more resistant to outliers than, say, the mean. What this means is if you have a sample of 10 numbers and they're all in the teens, and then you have one number in that sample that's a million, and you take the average is skewed. But if you take the median, it's better. So the median is more robust. Okay? Bootstrapping, what we're going to be looking at here, is a robust statistic for estimating confidence intervals. Okay, so I use this a lot when working with EEG and neuroscience data. So I'm just going to run this cell and we'll talk about it briefly. It's just generating perturbed sine waves right here. This is what it's doing. It's generating about 1,000 of these, and the bootstrapped algorithm is it samples with replacement 100 of these and flattens them down and averages them together. Okay, that's the idea. That's what all of this code is doing. We'll look at it in a second when we annotate it in Cython, but nothing too crazy. The mean and the variance, they're both here. Okay, great. That originally took 2.27 seconds. I'll expand this down here. We'll run this through the very basic Cython compilation, and we'll try running it again. So yeah, there's stuff all over the place in this one that we can improve, right? Like it's much more dense in terms of things it's doing. It's got a couple list comprehensions in there. There's tons of things going on. Okay, but again, we're faster just by compiling. Okay, so let's really quickly, I'll just throw in a couple of these, our new keywords that we've learned. Another one in here that is definitely an integer is b. I'm forgetting one thing, which is to import Cython, so I can have my cdef keyword. Okay, let's recompile. Okay, let's run it again. Have a look at the timing. Sip coffee. Okay, I don't think that was much faster at all. Maybe a little bit faster or in the same range, which is interesting because it means that the format of your problem matters a lot for this technique. Okay? So the next thing we can do, and I'm just going to copy and paste it in again, and I'm sure that you, as somebody working on this code, would figure this out eventually too, but we've got two pre-allocated arrays here that are of floats because we're working with floats in this particular case. Let's see how a memory view would actually tackle this problem. We have an error because I forgot to import. Okay, we need the NumPy keywords to declare our NumPy types inside of Cython. And we need just regular NumPy for our zeros creation here. Okay, it's compiling. We're getting a similar warning to before. I believe that's just because of my NumPy version. I wouldn't worry too much about that. And let's have a look at how much faster it is. So we are looking at, I'm going to predict, yep, because I've run this ahead of time and done the demo. It's basically the exact same. And the reason for that is actually that we're bouncing back and forth between NumPy and regular Python and using the sum function here. So kind of what's important to take from this example is a few things. One, if you want to stay in Python, we should be using Python's type hints as much as possible. Two, it's, Cython's not a silver bullet. It's not going to work for absolutely everything. And three, if you really wanted this code to be optimized, the way to do it is vectorization in NumPy or something like Numba. Okay. So not everything is going to be perfect, but it's still, there was significant speed ups. Okay. Because it scales. These are small problems. Okay, I'm going to quickly move on to problem three here because we've got a couple slides to go back in my presentation, and I think this is a powerful point here. In my original talk, this was my base sieve function. Okay, this is exactly as it was. It's complete, correct, it works. And if I run it through time it again on a sample of 10 million, what do we get for timing? Algorithm's quite simple. Nothing like you can go back to the previous talk for the definition of this. Um, Nothing too shocking. Okay. So one of the big things that I said that had changed, and we all agree, is ChatGPT, right? So what happens if I take this code that I wrote for that previous presentation and say, hey, Cythonize this, um, and what's the timing improvement? So this isn't just free in terms of, hey, this is an int and this is an int, this is an int. This is like free. You can log into ChatGPT right now. So this is what I got. This is the exact screenshot. It's defined I and marker, and it's changed my list comprehension to be a bit different and is using the list type from Cython. Okay, so underneath here, I've copy and pasted that in instead of the image. And the image is just to prove that it really is from native ChatGPT. I will compile it and I'll try running it and see what the speed up is. So before it was 2.13 seconds, and we're down to 1 second for free, right? How many times can I say free for increasing your speed? Okay. But what's interesting from this is if you go look at my previous talk, I went very far down the rabbit hole with this particular optimization because I was competing against a coworker who was very much a fan of C and C++. All of the staff members who are here know exactly who I'm talking about, and I wanted to make it as fast as possible. So we didn't get all the way down to the optimizations I eventually made. I mean, I could recompile this one and have a look and show you what this looks like. When I get to the end of the previous talk, there's no yellow left. I got it all white and all in compiled natively into C and C++, and it was still slower than just native C and C++, but still much faster than raw, just vanilla Python. Okay, so our conclusions from problem three, what we all expected. Cython, still good, is good, will forever be good. ChatGPT is pretty good at this for free, and it doesn't, and this is important for the future, it doesn't, do quite as good as someone digging really deeply into this function. Okay, so demo time over. That went pretty good. Post-demo discussion. So you should be convinced. I was convinced several examples ago when I was doing this for myself the first time in 2020, June, I believe. So go take a look at the main documentation for Python, not Python, for Cython. There's more examples in there with more complicated memory views that probably you would like to use in your data. You can go check out the Python documentation for the Alliance and our systems. It's going to be different than your local system, so please go and read that. And all of this generalizes to the cluster fully. And in the previous video, I cover exactly how to do that from the command line on a Gram login node and start running it. Okay, so takeaways, Python, still awesome, and we can get a lot of speed back with Cython. Annotate mode is super powerful and directs us exactly to where the code can be improved. And last but not least, new AI tools, ChatGPT, whatever Gemini things are new in the new hotness, lower the barrier to entry for taking up Cython. There's less of a burden on you, the researcher, to be aware of what goes on in C and C++ typing and typing systems. so you can pick it up even easier. And so thank you very much for your time and attention. I'll take some questions now.